Welcome back to our YouTube channel. Today, we have an exciting topic to dive into: deep learning and neural networks. Have you ever wondered how artificial intelligence is able to recognize images, translate languages, or even beat humans at complex games? Well, the answer lies in the power of deep learning and neural networks. In this video, we'll explain the fundamentals of deep learning, how neural networks work, and explore their wide-ranging applications. So let's get started. At the core of neural networks is the concept of a neuron, inspired by the structure of the human brain. Neurons are interconnected nodes that process and transmit information. In deep learning, we stack thousands or even millions of these artificial neurons together to form a network. Each artificial neuron, also known as a perceptron, receives input signals, processes them, and produces an output signal. These input signals can represent various features of the data we want our neural network to learn. For example, in image recognition, the input signals might correspond to pixel intensities. So, how does a neural network learn? It goes through a two-step process: training and inference. During training, the neural network is presented with labeled examples to learn from. It adjusts the connection strengths, or weights, between neurons to minimize the difference between its predicted outputs and the true labels. This process is called backpropagation, where the network learns to recognize patterns and features in the data. Deep learning takes things a step further by using multiple layers of neurons, forming what we call a deep neural network. Each layer builds upon the previous one, extracting increasingly complex features from the input data. The first layer might detect edges. The second layer combines edges to form shapes, and subsequent layers progressively identify more abstract concepts. This hierarchical representation allows deep learning models to capture intricate patterns and make accurate predictions. One crucial aspect of neural networks is the activation function. It introduces nonlinearity into the model, enabling the network to learn complex relationships between inputs and outputs. Activation functions like the sigmoid, tan, or ReLU, rectified linear unit, determine the output of a neuron based on its weighted sum of inputs. This nonlinear behavior enhances the network's ability to handle more intricate data representations. Now that we understand the basics, let's explore the vast applications of deep learning and neural networks. From computer vision to natural language processing and even self-driving cars, deep learning is revolutionizing various industries. It has enabled breakthroughs in image classification, object detection, speech recognition, and machine translation. Deep learning models have surpassed human performance in tasks like image recognition competitions and defeating world champions in board games like chess and Go. While deep learning has achieved remarkable successes, it still faces challenges. One of them is the need for massive amounts of labeled training data. Collecting and annotating such data can be time-consuming and costly. Additionally, the computational requirements of training deep neural networks can be substantial. However, researchers are actively addressing these challenges. They are developing techniques such as transfer learning, where pre-trained models can be adapted to new tasks, and exploring methods to make deep learning models more efficient and interpretable. The future of deep learning is incredibly promising. Researchers are constantly pushing the boundaries, exploring new architectures and algorithms to improve performance and efficiency. With the advent of more powerful hardware and the availability of large datasets, deep learning continues to evolve, leading to even more exciting applications. As deep learning becomes more prevalent in our lives, it's essential to address the issue of interpretability. Deep neural networks are often considered black boxes, making it challenging to understand how they arrive at their predictions. Researchers are actively working on techniques to make deep learning models more transparent and explainable. This transparency is crucial for building trust and ensuring ethical use of these technologies. The impact of deep learning is already evident in various fields. In healthcare, it is being used for early detection of diseases, medical imaging analysis, and personalized medicine. In finance, deep learning models help detect fraud and make better investment predictions. In transportation, they are powering self-driving cars, optimizing traffic flows, and improving navigation systems. The applications are vast and continue to expand. To further advance deep learning and neural networks, collaboration between academia, industry, and the wider research community is crucial. Ongoing research focuses on improving model generalization, reducing bias, addressing privacy concerns, and ensuring the responsible and ethical deployment of these powerful technologies. In summary, deep learning and neural networks are at the forefront of artificial intelligence. By emulating the structure and function of the human brain, these models can learn from data and make accurate predictions. From image recognition to natural language processing, the impact of deep learning is felt across numerous domains. So, next time you use voice assistants, interact with recommendation systems, or see autonomous vehicles, remember that deep learning and neural networks are working behind the scenes. I hope you found this video informative and that it sparked your curiosity to explore this fascinating field further. Thank you for watching. Don't forget to like, share, and subscribe to our channel for more exciting content like this. And if you have any questions or topics you'd like us to cover in future videos, please leave them in the comments below. Stay curious and keep learning. Until next time.